Detonation at Launch Complex 36. Blue Origin just lost a New Glenn first stage to a structural detonation at Launch Complex 36 that was never supposed to happen. 2 days ago, during a full 7-engine static fire of the booster named No It's Necessary, the vehicle experienced a high-frequency vibration event that transitioned into a catastrophic hull breach. This was not a propellant leak or a simple fire. It was a total structural collapse under the acoustic load of the BE4 engines. The telemetry suggests the airframe hit a resonance limit that the Pogo suppression system could not damp out. This failure destroys the hardware and the immediate timeline for Amazon's LEO constellation deployment. The BE4 pressure ceiling. To understand why this happened, you have to look at the BE4's oxygen-rich staged combustion cycle. Last year, Blue Origin pushed these engines to a certified thrust of 640,000 pounds, but that performance comes with extreme internal manifold pressures. In a staged combustion engine, the entire liquid oxygen flow passes through a pre-burner, creating a high-pressure environment that is notoriously difficult to stabilize. During the May 28th test, the engines were hitting 98% power when a pressure spike in the main oxidizer valve created a hydraulic hammer effect. This isn't a software bug. It is a physical constraint of moving that much mass through a 7-meter diameter thrust structure. Resonance and the Pogo problem. The most likely culprit for the fragmentation is Pogo oscillation, a feedback loop where the rocket structure vibrates at the same frequency as the propellant flow. Think of the New Glenn as a giant tuning fork. If the BE4 engines strike the right frequency, the entire fuel column starts to bounce up and down in the feed lines. This longitudinal vibration places massive stress on the aluminum lithium tank domes. Unlike the stainless steel used in other heavy-lift vehicles, this alloy lacks ductility and fails abruptly once its stress threshold is crossed. Data from the NG4 static fire indicates that the center engine's propellant line failed first, likely because it sits at the peak of the booster's vibrational node. The material failure reality. Blue Origin opted for aluminum lithium to maximize mass efficiency for reuse, but this incident highlights the trade-off. When a Pogo event occurs, the material doesn't bend or warn the ground crew, it shatters. This creates a narrow operating window for the BE4 engines. While the engines themselves may be flight-ready, the interface between the engines and the airframe is clearly hitting a limit. Even with a reinforced thrust frame, the mass of a 100-meter-tall rocket filled with cryogenic propellant creates a specific harmonic that is proving harder to solve than the marketing narrative suggested. This is an engineering bottleneck that cannot be patched with software. The signal under the noise. The LC-36 explosion reveals that New Glenn's current structural design is fundamentally incompatible with the maximum acoustic output of 7 BE4 engines at sea level. This isn't just about losing booster number 3. It is a verification that the Pogo suppression system and the aluminum lithium thrust frame have a lower tolerance than the mission requirements for heavy-lift constellations. For Blue Origin, this means the recovery rate is no longer the primary concern. They now face a mandatory structural redesign that will likely involve adding significant mass for dampening, which directly eats into the payload margins for the Amazon Kuiper missions and the NASA lunar contracts. This creates a strategic pivot point where Blue Origin must decide to either derate the engines and lose capacity or delay for 12 to 18 months for a full airframe reinforcement. Watch the upcoming hydrostatic tests of the 5th booster in late July. If they are running the tanks to lower pressures than before, it is a clear sign they are retreating from the BE4's maximum performance envelope to save the hardware. Subscribe for more.